So we've been talking about networks with nodes joined by links, but in the networks that we're involved in real life, we can be connected to other people in different ways through our family connections, through our work, through our political beliefs, and so on. So it's not just a question of whether one node is linked to another node, it's how are they linked. So links are multidimensional. There are different types of links. And to deal with this multidimensionality of links, people have developed various approaches. For example, the idea of networks of networks. So that is that a node can be in many networks at the same time. The kinship network, the employment network, the political network. And then another idea is that of hypernodes. So these are collections of nodes that can be linked to other collections of nodes. So the nodes are linked in a network, and then that network is itself linked to other networks. And we're going to consider a third approach that's been developed for looking at the multidimensionality of connections between nodes, which is known as Q analysis. And this isn't really a mainstream part of network science, but it's dealing with the same kinds of issues about connections between entities, the nodes in the network. So it's a good place to talk about it. And a key text in the idea of Q analysis is a book called Mathematical Structure in Human Affairs by Ron Atkin. This book came out in the 70s, and Atkin was active primarily in the 60s, 70s and 80s, talking about how Q analysis could be used to study a range of situations in human affairs. So, for example, chess positions and the study of modern art, and also political decisions. So one of the examples he gives is of a decision whether or not to move the students' bar in a university. So this is a political decision because there are various parties involved, the students' union, the administration of the university, the maintenance staff, and the works committee. So all these people have to be coordinated. Their different views on it have to be taken into account. And there are various issues at stake, like the cost of it. So the financial people have to have their say, how it will affect the environment due to the waste and the noise from the bar in the new location. And the maintenance committee will be the people, who are responsible for keeping it clean, and the building people about how it can be coordinated in with other building programs going on. So there's all sorts of people involved and issues concerned and trade-offs to be made. And Q analysis is designed to help study such situations. And of course, political systems and political decision making is a very important part of history and how societies evolve. So it certainly seems to have some relevance to the kinds of issues that we will come across in theoretical history. But that said, Q analysis isn't really something that has taken off or been widely adopted. And I think that's because the conclusions coming out of it at the end of the day are rather underwhelming. The mathematics is quite complex, and yet the practical value that comes out of it at the end of the day is difficult to discern. So we'll see as we go through the kind of thing it can do, and I think it's worth us looking at it because it has potential, even though it seems to lead to perhaps trivial conclusions at the moment. With further development, it may have more applications in theoretical history. And I think it's definitely a useful thing to have in our toolbox that we may one day draw upon when we come across situations where it will come into its own. So let's have a look at how it works. Okay, so here is a table showing a group of people: Alice, Bob, Carol, Duncan and Emma, A, B, C, D, E, and a set of interests that they might have: archery, bowling, cooking, dancing and eating out, A, B, C, D, E. And the ticks in the table show who has which interests. So Alice has interests of bowling, cooking, dancing and eating out. Bob has interests of archery, bowling, cooking and eating out, and so on. And what we're interested in is the mathematical structure of this situation. And the way Q analysis proceeds is to imagine that these interests are points in space or vertices, and each person is the geometrical figure or geometrical object that connects the points. So let's have a look at how that works. So if we start with Alice, she's got these interests, which I'll just shorten now: B, C, D and E. So Alice would be drawn like this. So there's Alice. She's this tetrahedron that connects the 4 points B, C, D and E. So it's a solid tetrahedron. And then Bob is also a tetrahedron. He's also got 4 points, so he looks like this. Bob is a tetrahedron connecting the points B, C, A and E. And now for Carol, she's only got 3 interests, so she's only 3 points. So she'll look like this. And similarly, Duncan is only 3 points. And lastly, Emma is just 2 points, cooking and eating out. So we've turned these people into these geometrical objects, and these geometrical objects are known as simplices, or each one is a simplex. A simplex, which is the convex shape made out of that number of points. So with 2 points you've got a line, with 3 points you've got a triangle, with 4 points you've got a tetrahedron, and then you'd go up to higher dimensions. With a line it's one-dimensional, so this is said to be a 1 simplex. With 3 points it's 2-dimensional, so that's a 2 simplex. And with 4 points it's 3-dimensional, so that's a 3 simplex. And then with higher numbers of points we'd need higher numbers of dimensions, but we would go to 4, 5, 6 simplexes and so on up. And while we've drawn these as the simplexes separated, of course these points are the same point. So here on Bob, he's got the point B, and Duncan's also got the point B. So these are actually the same points. So these simplices are connected via the points that they share in common. So let's just take an example with Alice and Carol, who share the 1 simplex DE. There's DE on Alice and there's DE on Carol. But Carol has also the point A, whereas Alice does not. So let's just draw how these two connect. So there's the simplex representing Alice, our tetrahedron, B, C, D and E. And then there's the simplex representing Carol, the triangle DEA. And they're connected along that 1 simplex. Now, there I've just drawn two of them, but all of the people here are going to be connected together. So let's just have a look at how that figure would look if we put them all, connected them all at their shared points. Okay, so this is what you'd get if all the simplices were joined together at their points that they share in common. And so all those simplices here are somewhere in that figure. You can see, for example, here's Carol, ADE. So she's that triangle in there in the figure. But we've also got, for example, the triangle BDE. And that triangle doesn't exist in this figure because, oh no, sorry, it's ABD, I should say, actually, ABD. So in fact, yes, I've missed out a line, haven't I? There should be that line. BDE definitely does exist in this figure because it's part of Alice. B, D and E. That triangle is there. It's A, B, E. There's none of these. Oh, hang on. ABD. ABD. So there's no one with A, B and D together. We're looking for A, B and D together. A, B and D. So there is no A, B and D. So that triangle that's kind of on the back here, A, B, D, that would actually not exist. It would just be hollow, that triangle, the face of it. And some other, you know, parts of the figure that don't exist would not be there. But within this, all those simplices are somewhere in that diagram. And this is known as a simplicial complex. A complex of simplices, the plural of simplex. And you can see then how perhaps this relates to issues we might get in theoretical history. I mentioned the political decision of moving the student bar. So in that case, these would be the different players, like the vice chancellor, the finance committee, the maintenance committee, the students' union. And then these would be issues like the attractiveness of the new venue, the environmental impacts, the cost impacts, and different actors down here would have different issues that they were interested in, and so you'd get this complex structure as to how they were connected via the issues that they that were important to each party. Or it could be these could be different countries here, and these could be different commodities, say, or different that they produce. So they might be connected in that way by producing the same commodities, or they might be connected by being members of different forms of international alliance, like the United Nations and NATO and the World Health Organization, and some would be members and some not. Or it could be countries involved in the First World War down here, and then the issues that were at stake in the war. So we could study the structural properties of that situation using this idea as seeing it as a simplicial complex. And of course, in reality, we wouldn't be drawing out these pictures. This is just to give us some intuition as to what this all means geometrically. But with lots and lots of players and lots of issues, it would be far too complicated for us to analyse. but we can see the same thing from the table, so that we can see from the table, we don't need to draw this picture of Alice and Carol. We can see from the table that Alice is joined to Carol at those 2 points, just by looking at it in the table. So let's just make a bit more space, get rid of this. Okay, one of the key ideas then of Q analysis is that of connection between two simplices. So we've already seen how Alice and Carol are connected at 2 points. And so we would say that Alice and Carol being connected at 2 points are connected by a 1 simplex. That's a 1 simplex with 2 points. Remember, 2 points defines a line which is a 1 simplex. So we would say that Alice and Carol are 1 connected. And in general, there's the idea of Q connection, where Q is the number, represents a number of connectedness of any 2 simplices. So we're interested in the Q connectivity structure of this. So we've just said Alice and Carol are 1 connected. Alice and Bob, well, they share 1, 2, 3 points. So Alice and Bob are 2 connected. And if you are 0 connected, that would just mean 0-dimensional connection, that you'd be connected at one point. So there's nobody here who's just 0 connected. Even Emma, although Emma is only a 1 simplex, she is 1 connected to Alice, being connected at those 2 points. And if you didn't have any points in common, then you wouldn't be Q connected at all, you'd be disconnected. Now when we see here that, say, someone like Duncan, he's 2 connected to Alice because he shares 3 points in common, but in fact he is really in a way just part of Alice, because if we draw Alice's tetrahedron again, there is B, C, D, E, then Duncan is on here already. He's okay, well it's not, I didn't do it very conveniently, but he's this one at the back, B, C, D. So if that whole thing is Alice, then Duncan is this triangle or 2 simplex at the back.
If the dashed line is at the back, BCD is actually at the front, but hopefully you get the idea.
So we would say that Duncan is a face of Alice. And similarly, we see that Emma is also a face of Alice, because she is CE, which is here. That's Emma. She is another face of Alice. She's a 1-dimensional face and Duncan is a 2-dimensional face. So to repeat, D is 2 connected to Alice, but he's also a 2 simplex face of Alice. And then we can talk about the connectivity of the whole complex. So a simplicial complex is Q connected if all the simplices are at least Q connected. So in this case of our simplicial complex, we have got that Carol is 1 connected to Alice, but by those 2 points. She is 1 connected to Bob by those 2 points. she's only 0 connected to Duncan via that, and she's 0 connected to Emma. So Carol is only 1 connected to the rest of the complex. There is a 1D connection between Carol and the rest of the complex, which is via both Bob and Alice. So this simplicial complex is 1 connected because Emma also is 1 connected into the complex through those 2 points she shares with Alice. Duncan is 2 connected, Carol is 1 connected, and Bob and Alice are also 2 connected. They share 3 points in common. So because every simplex is 1 connected, but it's a 1 connected complex, but not every simplex is 2 connected, so it's not a 2 connected complex. You can't get to every simplex via 2 connections. When you come to Carol, the only connection to her is a 1D1 simplex. So Q connection applies to any pair of simplices, and it also describes the connectivity of the structure as a whole. And then the key point from this is that information has a dimension. So information is itself Q-dimensional. So what do we mean by that? Well, if Carol and Alice both have interests in dancing and eating out, so they can discuss those issues. They can trade off one against the other. They can trade off those 2 things. Should we go dancing or should we go eating out? Or how much time should we spend on dancing versus how much time should we spend on eating out? Because both of them can deal with those issues, they can trade off those 2 issues. But those are the only 2 issues that they share. So that they can only do that kind of trade-off just between those 2 particular issues. So that is 1-dimensional information that they can share because there are 2 issues, so it's joined by a line, so we call that 1-dimensional information. But if we take Alice and Bob, they have got 3 things in common. So bowling, cooking and eating out. So they can discuss 3 things, they can juggle 3 things. So they can deal with 2-dimensional information. 2-dimensional because it's got 3 points. B, C and E. They can juggle those 3 issues. They can handle 2-dimensional information. And so the ability of information to move around this group of people depends upon the Q-connectedness of the simplicial complex. Because although, let's say, Carol is only 0 connected to Emma, because it's just eating out that they share in common. They don't have any other points in common, so that's just 1 point, so that makes it a 0-dimensional connection. So directly they can only share 0-dimensional information, but they can share 1-dimensional information via Alice because they are both one connected to Alice. So Emma can trade off cooking and eating out with Alice, and then Alice can trade off dancing and eating out with Carol. So there can be 1-dimensional information passed from Emma to Carol via Alice because they both have a 1D connection to Alice. But we cannot get 2-dimensional information through this simplicial complex because not everybody is 2 connected into the complex. Okay, so this is an example taken from some work I did many years ago, which has involved analysing the dynamics of military exercise. and Q analysis was one of the tools that I used for that. So this is based around the field headquarters, which contains has three characters in it, three people in it: the operations officer, the battle group engineer, and the engineer sergeant. So there are two simplices in this simplicial complex of two simplices joined together. And the operations officer, the operations are responsible for running the battle, fighting the battle, relaying the commands to the various subunits as to where to go and what to do. The engineers are responsible for things like laying down bridges to cross rivers, or building obstacles to obstruct the enemy, clearing minefields, things like that. And these people and various other functions as well come together in the field headquarters. And what you find is that when the battle group engineer disappears from the headquarters, there's a noticeable fall off in the quality of the interaction between the operations staff and the engineers function within the battle group. This would be so the information stops flowing so clearly as to the engineers don't have as good an understanding as to what the operation, how that's proceeding, and the operations don't have as much control over what the engineers are doing, or as much visibility as well of what the engineers are doing. And we can understand that as being due to the taking away of this simplex of the battle group engineer. So what I've shown is define them as simplices in terms of the vertices of being responsible for operations, being an officer, commissioned officer, being an engineer or concerned with engineering, being a non-commissioned officer, and having a managerial function within the battle group, so being a headquarters role. And you can see that the battle group engineer, who is a commissioned officer, is connected to the operations officer, who's also an officer, by being an officer and having a managerial headquarters function. And he's connected to the engineer sergeant by having a managerial headquarters function, and also by being an engineer. So when he is so at this point, there is this complex is one connected. There's a one-dimensional connection, one simplex connection there between the engineer sergeant and the battle group engineer, and there's a 1D connection, one connection between the battle group engineer and the operations staff. But when the battle group engineer goes away from the headquarters, as he sometimes has to do, to go out and visit his engineer troops out in the countryside, or go and see the commanding officer who is not in the main headquarters but in his own tactical headquarters out in a Land Rover somewhere with his 2 or 3 key staff. So the battle group engineer may have to go off and brief him, for example. So he disappears from the headquarters, and that reduces the connectivity of this simplicial complex to a zero connection just at one point. And so we can say that when you go from there to there, the complex is less connected, and that explains or describes the reduction in the amount or quality of information flowing between the engineer function and the operations function. And we can describe this connectivity structure through what is known as the structure vector, which shows the how many parts the complex divides into at different levels of Q connectivity. So in the first instance, we've got two simplices. There's the highest dimensionality of simplex here. So we consider at the level of Q connectivity, how many parts does this simplicial complex divide into? Well, there is no two connection here. There's only one connection. So this two-dimensional simplex of operations is a thing in its own right. It's not two connected to anything. That's a thing in its own right at the level of two connection. It's not two connected to anything, and nor is that. So we've got three different parts at the level of two connectivity. These aren't connected at two connections, so they're separate at the level of two connectivity. They make three different things. But then when we go down to consider one connection, well, ops is one connected to the battle group engineer, which is one connected to the engineer sergeant. So at the level of one connection, this simplicial complex is completely connected. It is just one component, one part. And then at the level of zero connection, it will also be one connected, because if you're one connected to something, you're also zero connected to it. If you're connected by 2 points, then you're also connected at 1 point. So at zero, if we look at the zero connection, it also makes one whole component. Whereas over here, the structure vector is at the level of two connection. That's one component, because it's not two connected to that, and that's a separate component. So we've now got two components at two connection, because there's nothing there. And then at the level of one connection, well, now, because the battle group engineers disappeared, they're only zero connected. So these are still separate at the level of one connection. So there's still two components.
But the simplices are zero connected. So at the level of zero connection, the complex forms a single component, giving a 1 in that part of the structure vector. Now, the last idea to mention is that of the conjugate complex. So in our original simplicial complex, we regarded the people, Alice, Bob, Carol, etc., as the simplices, and the interests, archery, bowling, cooking, etc., as the vertices. But we can invert this and regard the interests as the simplices and the people as the vertices. This gives a different complex, the conjugate complex, and we can analyze its structure in the same way, giving rise to an alternative set of insights into the structure of the system.
So to summarize, I suppose the problem with Q analysis is that while it gives you a picture of the structure of a situation, it's rather static. And although you can talk vaguely about information flow through the structure, there doesn't seem to be any quantifiable conclusions coming from that. So we're kind of waiting for the genius who can come along and show how we can take this framework and develop from it meaningful and tangible results that have real world implications.